Tuesday, 18 April 2023, Seattle, Washington. Well, it's been more and more talk about the path integral. And last time there was some reading from this volume 2 of the Feynman lectures in physics. That it was about section 3 that for about the flux of a vector field, what we were getting into, that the vector integral was defined, and so that Feynman begins to define the vector integral, the line integral of grad psi, nabla psi. And this is sort of relevant because it helps illustrate coming up after the line integral how it gets to the path integral. And so it'll be interesting to read what Feynman and of course Leighton and Sands, the other co-authors of these lecture notes, take up and put down as of the integral formulas involving the gradient, as I just quoted. The integral is a line integral from 1 to 2 along the curve gamma of the dot product of grad psi, a vector, with ds, another vector, which is an infinitesimal line element, of the curve gamma directed away from 1 and towards 2. You'll often find that physicists are a lot more free in their description of things in terms of the raw differential. And that the dynamical modelers are a lot more free in their things in terms of like x infinity or as the Markov sequence, for example, goes to infinity, that it has that value. And it's read into the notation. It means it formally is in accordance with our limits and in accordance these kind of very disjointed and cobbled together pieces that reflect this non-standard analysis. How it goes is that it's to be kept in mind that for hundreds of years it was the infinitesimal analysis, and that there was a very strong course for the curriculum for rigor, and rigor for the formalists is a very important and key thing for preventing the misapplication or the wrong step in this sort of a derivation of a thing that would result in nonsensical data, nonsensical derivations. And so the rigor of the time is built as about the standard analysis, and there's the complete ordered field, and the formulas is about after least upper bound, and after then for measure that there's the completeness of the real numbers, and then with regards to the usual framings of things in terms of continuous functions and the usual open topology, and there are others, of the topology of the points of the real line, of the point set of that the line is comprised of these points as their union together in these models, as for example where set theory is our foundation and upon it is built Russell's big axiom that infinity would be well founded, that otherwise according to Russell's paradox it's not, that's a particular opinion and an axiom, and that there's the axiom of the otherwise the regular well-foundedness of the sets. And then there's the axiom that the least upper bound exists for the complete ordered field in the set. And there's the axiom that the distance between 0 to 1 is measure 1.0, and as accords within these sigma algebras that are so established, and build that up about what makes a measure. And the rest of that afterwards is pretty much free of opinion in a sense, though there is, with regards to things like the fundamental theorem of the derivative and the fundamental theorem of the integral, about how those are built as the limit of things in terms of the Riemann sums, and that follow then closely after Newton's method and Leibniz's method, the integral calculus, insofar as how it goes then that's its rigor has been formalized, and formally that's its rigor. Its rigor being its strength and its guide. And so then when we talk about the raw differential, an infinitesimal element, it's with respect to that in quantities that is maintained that this infinitesimal element must be summed up and over all the infinitude of them, so many. Either concept, infinitesimal or infinity, kind of outright with regards to what otherwise results is, then we can talk about it in terms of a length or an area or a volume, a quantity that's so mensurated, measured, and having real analytical character that's a finite value. So it's not so much that physics got rid of infinities as that they're quite usual, and that the methods of mathematics keep them quite usual, and that the usual applications are a careful sort of conceit that it's not necessarily so that the rigor in establishing a formal proof of the validity of this derivation mathematically wouldn't be very uncomplicated. And then that gets into the non-standard analysis and then also the very particular applicability of various non-standard functions modeled as in the limit, in the continuum limit, Dirac's delta particularly, and that then going on forward, he's able to describe this. These are descriptive terms. So when he says that ds is the infinitesimal of s, that with regards to some other term, that the raw differential is only to be framed in terms of a ratio about what's the nil valent, the nil square, the nilpotent, this way. Another vector, which is an infinitesimal line element of the curve gamma directed away from 1 and towards 2, that with respect to that going in its, it shares the same direction as the curve at that point. It's the derivative. First, we should review what we mean by a line integral. Consider a scalar function, f x, y, z, in the curve gamma joining 2 points 1 and 2. We mark off the curve at a number of points and join these points by straight line segments as shown in figure 3.2. Each segment has a length ds sub I, where I is an index. It runs 1, 2, 3 by the line integral along gamma integral from 1 to 2 of f ds. We mean the limit of the sum is sigma of the fi delta s sub I, where f sub I is the value of the function at the ith segment. The limiting value is what the sum approaches as we add more and more segments in a sensible way, so the largest ds I goes to 0. And this is about what we read up to, and then here we're getting into some of the terms that go on in terms of the algebraic application of the term psi and grad about it in terms of the inner products, the dot product, and also about the arithmetics that's in the differences, where there are various reasons why the arithmetic of addition and indifferences are different things. The addition in multiplication and division are different things. The addition of the arithmetic of addition and subtraction vis-a-vis the arithmetic of multiplication and division are different things. They're all the same thing. It's called arithmetic, and in the numbers they work perfectly with regards to the complete ordered field, except for division by 0, of course. And they're the points at infinity are not members of the complete ordered field, which is an Archimedean field, where the non-Archimedean field may actually have infinite numbers or members as of a set in it. Here, though, it's that these particular properties of the inner product and scalar product result that they get back out numbers that happen to closely align with the length of these vectors in the same places, so that they can be equated, because members of a vector space can be scaled by a scalar, and so it results that it just defines families of vectors by their magnitudes, and these assignments of the intentionality, meaning the inner equals, same type and same value, work up this outer extensionality, different type, same value, in the real valued spaces. The integral in our theorem, equation 3.1, means the same thing, although it looks a little different. Instead of f, we have another scalar, the component of delta psi in the direction of ds. If we write delta psi sub t for this tangential component, it is clear that delta psi sub t ds equals delta psi dot ds, delta s. The integral in equation 3.1 means the sum of such terms. Now let's see why equation 3.1 is true. In chapter 1, we showed that the component of grad psi along a small displacement delta r was the rate of change of psi in the direction of delta r. Consider the line segment delta s from 1 to point A in figure 3.2 according to our definition. Delta psi 1 equals delta A minus delta 1, or psi A minus psi 1, grad psi 1 dot ds1. Also we have psi b minus psi a equals grad psi 2 dot delta s2. Now this is getting pretty familiar as we think about the development in the path integral, as we've been reading from Swanson's path integrals and quantum processes, that these are these path elements, and that the A and B reflect either the beginning or end, and the 1 and 2 represent any two infinitesimally distant points within that. Between A and B, there's an infinitude of points. If A and B is 1.0, then there's an exact infinitude of these points. That the points range from 1 to infinity, or 0 to infinity, and thus it results that F0 is FA and F infinity is FB in this extensionality. That F in infinitesimals is this way and F in units is this way. This is basically making a ratio between 1 and infinity. It's not the same thing as 0, though in the standard it is. Because infinity doesn't exist, and the limit of 1 over n as n goes to infinity is 0. Here, though, that's that the infinitesimals between 0 and 1 go as if they are from 0 to infinity. And it also has other strange properties in terms of that a well-ordering doesn't exist on the real numbers, though it's axiomatized to exist. No one can give an example unless it's this thing. It's shown that this sweep or this iota values are the only way that the numbers can be like this, because a Cartesian function it is not, and otherwise Cartesian functions would make it so uncountable that it's not. So it's very particular, and it gets all the way into the foundations of mathematics and how it's rigorous, and about why it's not the usual first course of the standard development, because all the rest of our analysis is built up about the complete order field in algebras, or Galois world, where let's start with a group and then we'll have the field of them together, when really it would as well be that you'd have these two funny groups that coincide in the middle, addition and division. Instead of addition and multiplication, the field. You have addition and division, the field. Because it's worked up that way, that it's most simple in terms of arithmetic and integers and small integers, that keeps things easy. Where, of course, grad psi 1 means the gradient evaluated at segment delta S1, and grad psi 2, the gradient evaluated at delta S2. If we add equations 3.3 and 3.4, we get psi b minus psi 1 equals grad psi 1 dot ds1 plus grad psi 2 dot ds2. You can see that if we keep adding such terms, we get the results psi 2 minus psi 1 equals the sum of grad psi I dot dsi. The left-hand side doesn't depend on how we choose our intervals. If 1 and 2 are kept always the same, so we can take the limit of the right-hand side. We have therefore proved equation 3.1. This is called the continuum limit, and it establishes that this metrizing ultrafilter, or otherwise these iota values exist or like so, have analytical character and they add up. And that without it being infinite, they don't, is the other takeaway. You can see that if we keep adding such terms, dot, 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 we get the result. Left-hand side doesn't depend, so we can take the limit of the right-hand side. We have therefore proved equation 3.1. You can see from our proof that just as the equality doesn't depend on how the points A, B, C are chosen, similarly it doesn't depend on what we choose for the curve gamma to join 1 and 2. Our theorem is correct for any curve from 1 to 2. It's not uncomplicated necessarily. The curve here is a curve that is a classical curve and doesn't admit asymptotes. It doesn't have a circle. It doesn't have anything that a line perpendicular to the curve would ever cross another line perpendicular to the curve, or rather the curve itself. Though I suppose that's not true. And also be vertical. Within a given region, I guess, is what then gets into expressing what is the measure of curvature. Vis-a-vis that the spiral space-filling curve has a curvature, it's 1 over r, radius. With respect to the usual measures of curvature, are rather inverse the usual interpretations of the sharpness of curvature. these are things left out because we live in a world of Cartesian coordinates. These functions and their usual developments is about the partial differentials and all these things that add back up to the vector spaces, which make things easy about the orthonormal vector base and all the functions of the vector space. We can see from our proof that just as equality doesn't depend on how the points A, B, C are chosen, similarly it doesn't depend on what we choose for the curve gamma to join 1 and 2. Our theorem is correct for any curve from 1 to 2. One remark on notation. You'll see that there's no confusion if we write, for convenience, grad psi.ds equals grad psi.ds about the quantity grad psi and leaving that out as algebraic terms, because grad and psi always have to go together. There's not like the raw gradient vis-a-vis the raw differential here in this context. With this notation, our theorem is psi2 minus psi1 equals the integral from 1 to 2 of grad psi.ds. The flux of a vector field. Here begins section 3.2. It starts with figure 3.3. The closed surface S defines the volume V. The unit vector n is the outward normal to the surface element dA area, and h is the heat flow vector at the surface element. So given that it's absolute zero outside and positive heat inside is the heat flow vector at the surface element, is one way to express that until reaching equilibrium, the heat always conducts from an area of greater heat to an area of lesser heat. It could be negative, thus that there. Though it says the outward normal is the outward normal is either thus positive or negative, vis-a-vis whether it's an inward or outward normal, and always positive. All right. And the surface is a point set in the higher dimension that it encompasses. If it's closed, it's a point set in the same space that must support the volume. And the volume is just the point set interior to that. Before we consider our next integral theorem, a theorem about the divergence, we'd like to study a certain idea which has an easily understood physical significance in the case of heat flow. We define the vector h, which represents the heat that flows through a unit area in a unit time. Suppose that inside a block of material we have some closed surface S which encloses a volume V. We'd like to find out how much heat is flowing out of this volume. We can, of course, find it by calculating the total heat flow out of the surface S. This represents basically the boundary. And for Mogan, as we're reading the non-linear electromechanical effects and applications, it's this configuration space in the mapping of the propagation from space to space as over a surface, that those surfaces are as connected, and it's basically that the surface is two surfaces, the inside surface and the outside surface, and they're the same point set, but the one is as connected to the inside and the other is connected to the outside. With respect to otherwise, the idea is that the surface is connected to both sides. It's a boundary, but as well either side some degenerate boundary that otherwise would only reflect or block things. There's no notion of any internal surface of the volume. We write dA for the area of an element of the surface. The symbol stands for a two-dimensional differential. If, for instance, the area happened to be in the xy plane, we would have dA equals dx dy. Later we shall have integrals over volume, and for those it is convenient to consider a differential volume that is a little cube. So when we write dv, we mean dv equals dx dy dz. Some people like to write d squared a instead of dA to remind themselves that it's kind of a second order quantity. They would also write d squared v instead of dv. We use a simpler notation, assume that you can remember that an area has two dimensions and a volume has three. The heat flow out through the surface element, dA, is the area times the component of h perpendicular to dA. We have already defined n as a unit vector pointing outward at right angles to the surface. The component of h that we want is h sub n equals h dot n. The heat flow out through dA is then h dot n dA. And we don't figure that there's cases that, for example, in the dimpled or very concave, What if the heat vector points all the way out from one element and points back into the interior surface, so it's if it's never left? Well, that would be a differential system, a differential equation in terms of those parts in that region, vis-a-vis what happens when it crosses the outer surface and back through the other outer surface and back into the inside of the volume. Is just an example that otherwise is simpler when it's convex, this volume, and for example that it's spherical, because otherwise there are any number of ways to consider how the vectors would not all be inside or outside the circle, or the sphere rather, even given that they're all positive or negative or not. The heat flow out through the surface element dA is the area times the component of H perpendicular to dA. It's Cartesian in this sense. It's basically geometric. We have already defined n as a unit vector pointing outward at right angles to the surface. The component of H that we want is H sub n equals H dot n. The heat flow out through dA is then H dot n dA. To get the total heat flow through any surface, we sum this contribution. We sum the contributions from all the elements of the surface. In other words, we integrate 3.10 H dot n dA over the whole surface. Total heat flow out through S equals the integral of over S, the surface, H dot n dA, with some convexity conditions or otherwise that it's not reticulated and this kind of thing. With regards to the reticle as like a focus and represents a locus with regards to the locus. We are also going to call the surface integral the flux of H through the surface. Originally the word flux meant flow, so that the surface integral just means the flow of H through the surface. We may think H is the current density of heat flow, and the surface integral of it is the total heat content current directed out of the surface. That is the thermal energy per unit time, joules per second. So this gets into notions of the differentiation between the words flux and flow, and also about how we have our fluid models that apply to our electrical model and our model of light and our model of in pretty much any kind of flow or current, and for the electrical and for the fluids in the fluid phase of matter. And as with regard to then the flux is the flow or current or any kind of passage in terms of the counts of these particles through a surface that it defines current, just like we do in the electromagnetism section of the first year of physics class in college that's for electricity and magnetism. But its current is by area. The coulombs or what or amperes both reflect flow of electron holes across the surface. And then, as with regards to some previous talks we've had about the path integral and about the eddies and the linear and nonlinear components and contributions, and that this is just sort of an instantaneous average at every single time. But it's, however, it could still be added up in the infinitely fast as long as it maintains that average, that it could be going in all directions at once, yet still just maintaining a general overall propensity that charge or the force carrier passes through this otherwise homogeneous surface, indistinguishable from all the other surfaces. That's sort of like the Pauli principle, for that particles do not occupy the same space and that they're indistinguishable, that so these areas are each separate to be summed up all together in terms of how they make a sigma algebra for measure, that it works out this way for each of these models of flow and flux. And then I'll be curious what Feynman says when he says it was defined as flow, that flux was defined. If flux, as I use it, which means the fleeting outward as of light, like that light is always only breaking or deceleration, and that flow is always only ever viscous, and liquid, that I'd be curious if there's any other meaning than that, because that's the meaning I assigned to it. That they otherwise are indistinguishable terms and interchangeable terms, though that under this convention they're not interchangeable terms, flux and flow. They do have equity interpretable models, more or less, though, with regards to various reversals and reciprocities, where they model the same things. The heat flow out through dA is then h dot nDA. To get the total heat flow through any surface, we sum the contributions from all the elements of the surface. We integrate over the whole surface. Total heat flow outward through S equals the integral over S h dot nDA. We're also going to call the surface integral the flux of h dot dot dot. We'd like to generalize this idea to the case where the vector does not represent the flow of anything. For example, it might be the electric field. So this gets into statics vis-a-vis dynamics and magnitudes of these vectors as quantities, where basically the vectors here might have meaning in the direction if they're not flow in terms of phase or polarization, but they're standing quantities, not moving quantities. Where the vector does not represent the flow of anything, for instance, it might be the electric field. We can certainly still integrate the normal component of the electrical field over an area if we wish. Although it's not the flow of anything, we will still call it the flux. And we say flux of E through the surface S equals integral S E the electrical field dot nDA. And so here flux is that in terms of a standing wave, and as we've been talking about all this waves on out to the theory of some potentials of resonances, that at any given time that electron or electron hole or what it was that would be encountered is in terms of encountering anything in the electric field, could be anywhere. That's the usual Heisenberg uncertainty principle, that the according to the energy of the electron, it could be anywhere. But then this flux then sort of does represent the fleeting and the super side of this model of flow, and that again it can be read that when he says flux here and he says, okay, we don't mean flow anymore, but it is still like flux, and then in the interpretation that I've been just giving, it actually still is, which is nice. So I'll leave that like so. We generalize the word flux to mean the surface integral of the normal component of a vector. In these models that happen to be guided and driven by certain physical principles of certain physical processes, thus that have certain physical properties, that these here is that flux like so would otherwise just be called the integral of the vector component, integral of the vector field. Yeah, otherwise it doesn't need a name. And returning to the special case of heat flow, let us take a situation in which heat is conserved. For example, imagine some material in which after initial heating no further heat energy is generated or absorbed. And so here, we start with a model where there's basically there might be a source of heat inside, or there might not. There might be something that's exothermic and gives off heat, or endothermic and takes in heat, converting it to another state of matter, or converting it in energy in a junction, or transmitting it out as via a different force carrier, like light or charge, or whatever else carries energy, or the kinetic, or as of converting that stored and potential energy to displacement of the object overall. Jumping. But here is he's just illustrating, of course, that the particular usual case that begins at an equilibrium and goes to an equilibrium is, according to the conservation law, around these boundaries that are defined by continuity laws on either side of the boundary. For example, imagine some material in which after initial heating no further heat energy is generated or absorbed. Then if there is a net heat flow out of a closed surface, the heat content of the volume inside must decrease. Assuming that the inside and outside start at the same temperature and then heat was applied inside. Then if there is a net heat flow out of a closed surface, the heat content of the volume inside must decrease. So in circumstances in which the heat would be conserved, we say that the integral of S h dot nDA equals negative dq dt, where q is the heat inside the surface, and T is time. And that dq is a function in Q, thus that it has a well-defined derivative as vis-a-vis a quantity. Because there's only some particular quantities and functions associated with them, associated with particular times, and associated with particular contrived areas and volumes that would result that there's no internal reservoir, or there's no internal surfaces that have their own integrals and their own surfaces in terms of those. That here, basically the generalized surface is infinitely many shells, spherical shells, about an origin, and so that it's all the way through each of those. Here, though, as he notes, it's just dq over dt, or rather negative dq over dt, the potential for the heat to escape the surface. The heat flux out of S is equal to minus the rate of change with respect to time of the total heat Q inside of S. This interpretation is possible because we are speaking of heat flow, and also because we suppose that the heat was conserved. We cannot, of course, speak of the total heat inside the volume if heat were being generated there. It also sort of assumes that there's no heat outside. And this kind of gets into how you define the thermal laws calorie, which first laws calorie, which we read from Feynman in one of these other lecture notes. And it was along the lines of like 1 calorie is in terms of what converts one of the inner to one of the outer, and results that when it reaches equilibrium, that's 1 calorie. And it's basically logarithmic as about calories. Whereas absolute zero, or second thermal laws calorie, is a different thing. And so the calorie is kind of an overloaded and undefined term in terms of quantity of heat with respect to thermal first law or thermal second law definition of calorie. Here it's like the first thermal law calorie, because it's assuming that the inside and outside start at the same temperature, heat was applied to the inside, they'll equilibrate, and that the outside is so much greater that it will only reach an equilibrium and not really boil the ocean, as it were. Though it does, of course, as it dissipates, as it attenuates, it adds to the floor of what could raise the heat of the ocean. This interpretation is possible because we are speaking of heat flow, and also because we suppose that the heat was conserved. We cannot, of course, speak of the total heat inside the volume if heat were being generated there. Well, you could have it as a function over time. It'd just be a more complicated function, and it wouldn't be a simple derivative as with respect to the time term and being independent of the time term with respect to the dq over dt. Now we should point out an interesting fact about the flux of any vector. You may think of the heat flow vector if you wish, but what we say will be true for any vector field C. Imagine we have a closed surface S that encloses the volume V. We now separate the volume into two parts by some kind of a cut, as in figure 3.4. Now we have two closed surfaces and volumes. The volume V1 is enclosed in the surface S1, which is made up part of the original surface SA, and the surface of the cut SAB. The volume V2 is enclosed by S2, which is made up the rest of the original surface SB and closed off by the cut SAB. Now consider, so this is a cut through the middle, and the contour around it also is on the outer surface. So it's not just like an inner spherical shell we're talking about. It's more as if there was a pipe and there's left and right the pipe vis-a-vis heat loss from a pipe, like a hot water pipe. A volume V contained inside the surface S is divided into two pieces by a cut at the surface SAB. We now have the volume V1 enclosed in surface S1 equals SA plus SAB, and the volume V2 enclosed in surface S2 equals SB plus SAB. Following question. Now consider the following question. Suppose we calculate the flux out through surface S1 and add it to the flux through surface S2. Does the sum equal the flux through the whole surface that we started with? The answer is yes. Because, why? No, it does not seem so. it's contrived that it would be so in terms of the otherwise indistinguishable, about like the Pauli principle, and these two sides are just distinct and indistinguishable in equipartitioning. So here it seems that his answer being yes is an opinion, because otherwise we can contrive it that, for example, there's some contrivance where S1 and S2 would basically have any kind of interaction terms. There's no interaction terms to follow. All right, then. The answer is yes. The flux through the part of the surfaces SAB common to both S1 and S2 just exactly cancels out. For the flux of the vector C out of V, we can write flux through S1 equals integral SA C dot dN dA plus SAB C dot dN dA and 1 dA. And for the flux out of V2, flux through S2 equals integral of SB C dot NDA plus integral of SAB C dot N2 dA. Note that in the second integral we've written n sub 1 for the outward normal from SAB when it belongs to S sub 1 and n sub 2 when it belongs to S2 as shown in figure 3.4. Clearly n1 equals negative n2, so that integral of SAB C dot N1 dA equals negative the integral of SAB C dot N2 dA. If we now add equations dot dot dot, we see that the sum of the fluxes through S1 and S2 is just the sum of two integrals which taken together give the flux through the original surface S equals SA plus SB. Note the flux through the complete outer surface S can be considered as the sum of fluxes from the two pieces in which the volume is broken. We can similarly subdivide again, say by cutting V1 into two pieces. As long as you're not considering any inner boundary, because these terms, though they cancel the flow across both sides of the boundary, there is that edge on the outside with respect to any irradiating terms that have interaction terms that curve or drive them in or out of that surface would be a removable discontinuity. Or measure zero in area terms. Thus, as soon as we change this contrivance to say, well, what if we replace that section of pipe with a section with different thermal character, and then consider that as a surface, then that would be a different thing. This is uniformity and homogeneity, and it's clear and it's fine and it's all put together. Let's see where it's going with it. So we see that the flux, so for any way of dividing the original volume, it must be generally true that the flux through the outer surface, which is the original integral, is equal to a sum of the fluxes out of all the little interior pieces. And that's more than less the same as the fact that there's the integrable regions itself. And there's any number of ways to make a sigma algebra, and any of these subsets that so add up and make the same kind of sigma algebra. As far as analysis is concerned, it's all the same thing. 3.3, the flux from a cube, Gauss's theorem. We now take the special case of a small cube, and he says the following development applies equally well to any rectangular parallelepiped. We now take the special case of a small cube and find an interesting formula for the flux out of it. Consider a cube whose edges are lined up with the axes is in figure 3.5. So the XYZ and the cube is coming out of the page in X, Y, and Z, thus that Z is drawn down and to the left, and that delta Z is outward of the page, and that X and Y are the usual placement there. Now sometimes when you draw the Z dimension as via the methods of perspective or offset, Z order, that the invisible lines are written dashes and the visible lines are written solid to avoid otherwise the optical illusion of it looks either way with regards to the fixed Z order, lack of perspective. That here he's just drawn a cube and it's in X, Y, and Z, and then he identifies some. He identifies a vector C, and it's in only X, Y. Let us suppose that the coordinates of the corner nearest the origin are X, Y, Z. Let delta X be the length of the cube in the X direction, delta Y be the length in the Y direction, delta Z be the length in the Z direction. We wish to find the flux of a vector field C through the surface of the cube. We shall do this by making a sum of the fluxes through each of the six faces. First, consider the face marked 1 in the figure. The flux outward on this face is the negative of the x component of c integrated over the area of the force. This flux is negative integral cx dy dz. Since we're considering a small cube, we can approximate this integral by the value of cx at the center of the face, which we call the point 1 multiplied the area of the face, delta y delta z. So this is what we call a linearization, as we've been talking about in the differential geometry of sort, because it's very contrived to this setting, and lots of things that look very close to it in terms of being topologically very near to being the same and having the same kind of structure and symmetries, and with regards to other things that go on around it in various media in terms of other interactions, have that given that the source could vary about, besides this contrived vector that we're assuming that everything comes straight out of the faces, that there's no internal structure to this cube. Enough said. Flux out of 1 equals negative cz1 delta y delta z, cx1 delta y delta z. Similarly, for the flux out of face 2, we write flux out of 2 equals cx2 delta y delta z. Now cx1 and cx2 are in general slightly different. If x is small enough, we can write, if delta x is small enough, we can write cx2 equals cx1 plus partial of dcx over dx delta x. Again, linearizations resulting what would be at best numerical methods with the asymptotics. But carrying on, there are of course many more terms, but they will involve delta sub x squared and higher powers, and so will be negligible if we consider only the limit of small x. This is linear. And in this setting, we've been reading a lot from nonlinear electromechanical effects and applications about the higher order terms and how they exist. When you have more than one field and any number of interaction of terms and any matters of internal structure, it's not linear. But this is a means to make it, it's development. So the flux through face 2 is flux out of 2 equals, in brackets, c sub x1 plus partial of dcx over dx delta x times delta y delta z. Something fluxes for faces 1 and 2, flux out of 1 and 2 equals delta cx over dx, delta x, delta y, delta z. So he's established kind of the symmetry condition. And so then that, with regards to what's above, how he's established kind of a conservation condition, that then he's established that kind of like when it's spherical, it's this way, and kind of like when it's cubical, this way. So as long as our vanishing elements are both kind of like spherical and cubical, or don't break anything with regards to curvature or the quadrature, then it might have enough backbone to flex and stand up straight. So the flux through face 2 is dot dot dot. Summing the fluxes for faces 1 and 2, we get flux out of 1 and 2 equals dot dot dot. The derivative should really be evaluated at the center of face 1, that is at x comma y plus delta y over 2, z plus delta z over 2. But in the limit of an infinitesimal cube, we make a negligible error if we evaluate it at the corner, x, y, z. This is basically squares versus diamonds, and makes for why that in the quadrature that needs to be held up if it came to be so that it needed to be averaged over terms, like that. If a particle was a small square and spinning all the time, that it would be treated either like a circle or as otherwise. These are particulars with regards to the, usually in the linear and classical, it's easy to see how this is so, and it's fine. In the limit of an infinitesimal cube, we make a negligible error if we evaluate it at the corner x, y, z. This is like then with regards to the similar to the previous development is like in the negligible or removable discontinuity about where the cut of the surface touches the outer surface, it's negligible. Though that's just because it's assumed to have zero analytical character, and not some non-measurable analytical character, which might be non-zero, or otherwise that the boundary itself has an effect, or any of these other interacting terms, or any other internal structure, which would represent an infinite regress of these things with regards to the internal structure, which should be all right. Applying the same reasoning to each of the other pairs of faces, we have flux out of 3 and 4 equals partial of dcx over dcy, dx dyz, and flux out of 5 and 6 equals partial of dcz over dz, dx dy dz. The total flux through all the faces is the sum of these terms. We find that the integral of the cube of c dot nda equals the sum of dcx over dx plus dcy over dy plus dcz over dz of delta x delta y delta z. And the sum of the derivatives is just grad dot c. Also, delta x delta y delta z equals delta v, the volume of the cube. So we can say that for an infinitesimal cube, the integral over the surface of c dot nda equals grad dot c quantity times delta v. Volume. We have shown that the outward flux from the surface of an infinitesimal cube is equal to the divergence of the vector multiplied by the volume of the cube. We now see the meaning of the divergence of a vector. The divergence of a vector of the point P is the flux, the outgoing flow of C per unit volume in the neighborhood of P. So with respect to gradient, it's sort of just this higher order notion of gradient, where a gradient is the normal with respect to it's the normal to all the other terms which go away from the maximum difference, and that is this generalization with respect to volume. Divergence. The divergence of a vector at the point P is the flux, the outgoing flow of C per unit volume in the neighborhood of P. We have connected the divergence of C to the flux of C out of each infinitesimal volume. For any finite volume, we can use the fact we proved above that the total flux from a volume is the sum of the fluxes out of each part. We can, that is, integrate the divergence over the entire volume. This gives us a theorem that the integral of the normal component of any vector over any closed surface can also be written as the integral of the divergence of the vector over the volume enclosed in the surface. This theorem is named after Gauss. Gauss's theorem is the integral of SC dot NdA equals the integral V of grad dot C dV, where S is any closed surface and V is the volume inside it that has no internal structure, no interacting terms, no volumes inside it, and otherwise that the flux is constant. Then that with regards to the field at the surface, that it's a constant. And that the radiation at any point is just an instantaneous value, and it might or might not be the value over time, or the integral over time, as simply multiplying that rate by the differences in time. Here with regards to how to explain that in the units, that it is largely a matter of internal structure, and possibly any assumption about the attenuation and dissipation that it's uniform as from a point on the inside, vis-a-vis an abstract uniformly radiating sphere or an abstract uniformly glowing cube that is not so. Let's see, then in section 3.4, he begins heat conduction, the diffusion equation. So now I've been framing things quite a bit in terms of the restitutive and oscillating and dissipative and attenuating. And so the diffusion is an example that basically reflects there's a given point in its origin, and reflects that diffusion will have that the given difference between that point's contents, its value, and a sphere containing it, a ball containing it, that the diffusion will fill a spherical area at a constant rate of time. That is to say, any given distance from the point will have the same diffused value as any other point so distant from the origin. It's a growing sphere as about this, the change between any outward flowing flux from a point or arbitrarily small sphere, each of the outer spheres that contain it, until such time as it reaches a restitutive or oscillating boundary, or it is dissipated as it is attenuated to the floor, or zero, with regards to, for example, thermal first law or thermal second law, and they're different definitions of the calorie. Let's consider an example of the use of this theorem just to get familiar with it. Suppose we take again the case of heat flow and say a metal. Assuming a metal, it may be a perfect conductor of heat and electricity. It is kind of like so. Suppose we have a simple situation in which all the heat has been previously put in and the body is just cooling off. There are no sources of heat, so that heat is conserved. Then how much heat is there inside some chosen volume at any time? It must be decreasing by just the amount that flows out of the surface of the volume. If our volume is a little cube, we would write following equation 3.17, heat out equals the integral of the cube, h dot nda equals grad dot h delta v. But this must equal the rate of loss of the heat inside the cube. If Q is the heat per unit volume, the heat in the cube is Q delta V, and the rate of loss is negative d of dt Q delta V equals negative dq dt delta V. Comparing 3.19 and 3.20, we see that negative dq over dt equals grad dot h. Take careful note of the form of this equation. The form appears often in physics. It expresses a conservation law. Here, the conservation of heat. We have expressed the same physical fact in another way, equation 3.13. Here we have the differential form of conservation equation, while equation 3.13 is the integral form. We have obtained equation 3.21 by applying equation 3.13 to an infinitesimal cube. We can also go the other way for big volume V bounded by S. Gauss's law says that integral of S, h dot nda equals integral of grad dot h dv. Using 3.21, the integral on the right-hand side is found to be just negative dq dt, and again we have equation 3.13. Now let's consider a different case. Imagine that we have a block of material and that inside it there is a very tiny hole in which some chemical reaction is taking place and generating heat. We're going to imagine there are wires running into a tiny resistor as being heated by an electric current. We shall suppose that the heat is generated practically at a point and let W represent the energy liberated per second at that point. We shall suppose that in the rest of the volume heat is conserved. The heat generation has been going on for a long time, so that now the temperature is no longer changing anywhere. Problem is, what does the heat vector H look like at various places in the metal? How much heat flow is there at each point? All right, well, so now we're getting into these spheres and the diffusion of the heat. And so it's interesting to consider how this, kind of like in the development of the path integral, we got into the integral of the force applied and called that, for the force J, we called that the integral called the I. And then we took the derivative of that back again to add it back to what's standing up this path integral. And so here it's a little bit similar, how there's this kind of jimmying either way of, well, this is what the integral looks like according to grad, and this is what the differential looks like according to geometry. And so what I'll be curious to figure out is how to work out that this makes it so for some very, very contrived things, but then there's some very, very other simple and contrived things that would basically be pathological cases for this derivation. And so what I'd be wanting to figure out is what are the cases where the pathological cases for this derivation of Gauss's law were still yet more natural. And so how does it work up that there's built out a sort of mensuration with regards to that, a generally apropos nonlinear category, or otherwise how to make it so that it sort of leaves a placeholder for what would happen when you have a infinitesimal box, which is very usual and useful in the Cartesian coordinates, vis-a-vis the infinitesimal sphere, or what happens when there are eternal bodies, or what happens when there's an oscillation, restitution, or wave in this with regards to then how those radiate. And from a context, everything from gravitational waves to matter waves to temperature and thermal conductivity with regards to both thermal first law and thermal second law. These are kind of some interesting things that I'm automatically taking away from this development of what's pretty usual and about that the derivative and the integral are inverse operations, and so if you a given solution to derivative's integral is also, as for that integral's derivative, a point there as about it, if you take adding that or computing that out over some unit normal. And so where that isn't exactly so is something to be figured out, basically with regards to the focus of things and the locus of things, and about how then there's to be applied this the annulus and meniscus, basically, and the cusp, with regards to then that also is the thing going on with some of these notions of the path integral and the curve, and the curve out of the plane, or a spiral, that the curve and the spiral are different because the length of the path in the spiral isn't necessarily longer than that in the curve, but it covers more of a volume, it encloses more of a volume. And how that is as it goes from 0 dimensions and one-dimensional, these vacuous and trivial cases, out through the 2-dimensional, the planar, which is so quadrature, and then out through all the higher dimensions to the infinite dimensional. These are the kinds of things that I might get into, how to revisit and how to annotate derivations. So following from these derivations, how to equip them with certain other derivations which provide them greater tractability or greater resiliency, basically providing a sensible fungibility about what are the pathological cases of Feynman and Gauss that have natural solutions, and where it would be apropos that those are general and in place. And looking back to Swanson, where he left off in formula 3.34, it's Lagrangian of PQ, the position of momentum, equals PQ dot, the function of P, or this value with respect to Q dot, it's dq dt, minus P squared over 2m, minus VQ, is this potential, plus JTQ, the force over time as times the momentum as it accumulates. Of course, there are many restrictions on VQ that are necessary in order to have a sensible quantum theory. And so I haven't read much from the quantum process today. I was mostly reading a few lecture notes about some preliminaries from Feynman about the Gauss's derivation and what its linearisations are, and that there are several of them, and that they're involved with differential systems. And the exponential is not the only function that is its own antiderivative, which is so important and critical in all this Gaussian analysis. That the derivative and integral admit a single solution of a form of a function that is its own antiderivative, because the spiral space filling curve as a function and this equivalency, the iota values as a function, is also its own antiderivative. It's not a standard function, but it's also its own antiderivative. So the entirety of exponential analysis and complex analysis about this Gaussian branch and all this work of Gauss suddenly is doubled, in sort of doubling space, because no longer is e to the x the only function that's its own antiderivative, and thus for the operator calculus establishing the commutators as about it. that there are many restrictions on the potential field Q that are necessary in order to have a sensible quantum theory. That what is required is to add this other branch to catch most of the rest of those cases. In what follows, it will be assumed that these conditions are met. It should, however, be borne in mind that the manipulations presented here are of a formal nature and can disguise many of the difficulties that may be encountered in finding interacting theories. And so, just like I have been harping upon, Swanson carefully harps upon the fact that the derivation and the development must be in terms of its linearisations and approximations and its use of initial terms of series and its operations on lowering orders and all these other things that enable it to become sensible and then fungible to get a grip, and then even tractable, that it's possible to actually maintain these things symbolically without an explosion in forms diagrammatically. That what it points to is that for singularity theory and that for invariant theory and for the measure of curvature, it's like, as far as gauge theory knows, it's like what's the curvature that defines the gauge? That is our gauge theory called R gauge, and its curvature is 1 over R. Again, it's this spiral space filling curve as an original thing, which is very central, very, very central. Well, all right then. Have a great day, and here's the globe is spinning. So long.